All right, so today I want to talk about the definition of the derivative of a function. Um, very formally, it's defined in terms of limits. The limit as f prime, which is our symbol for the derivative, is the limit as h approaches 0 of f of x plus h minus f of x over h, as I have written here. This is a lot of symbols to remember, but it's not too hard to unpack from the idea of slope as just change in y over change in x. And if you draw a diagram, you can see why it fits this interpretation. The idea is that we have this graph of x, and then at some point x, you can take this little gap that's h wide, and then you can take this. Here you have this point, which is x comma f of x. Then you have this point, which is x plus h comma f of x plus h. And then you can just do slope between those 2 points. Right, so what's the slope between those points? Well, it's the change in y divided by the change in x, which the x's cancel on the bottom, and it simplifies to exactly what we wrote up above. So this is the idea of slope between 2 points on your function, right? The derivative gives us then, so what's the deal then with this limit? Well, the derivative is saying, now let h go to 0. So let those 2 points, take the limit as those 2 points converge upon just becoming the same point. And that will give you the slope of the tangent line, right? So as h goes to 0, then the 2 points become arbitrarily close. Right, because we're going to set h to 0. So this point kind of walks down here to the other point, and the slope converges to the slope of the tangent line. So this is the definition of the derivative, just written out for a arbitrary function f of x. I want to see now what this looks like in a specific example. So a great thing to do when you're trying out a new technique is try it in a case where you already know the answer, right? So let's look at a tangent line to a circle, right? So this is the easiest shape to find the tangent line to. Let's say even better, just to make it a little cleaner, let's say a unit circle. Right, so why is a unit circle not too bad to find a tangent line to? Well, if you're at point x comma y, right, think back to just basic geometry, right? How do you find a tangent line to a circle? Well, the tangent line is always going to be perpendicular to the radius of a circle, right? So this isn't anything from calculus, right? This is really just from geometry, right? If you have a if you draw to find the tangent to a circle at a point, just draw the radius and then take the line perpendicular to the radius. That's the tangent line of the circle. So here you could say, okay, the radius slope, well, the point is x comma y. So the radius slope is y over x. So the tangent then is perpendicular to that. So the tangent slope should be negative reciprocal of what we just wrote down, right? Because how do you do a perpendicular? You take a negative reciprocal. Right? So that's the slope of the tangent line to a circle. So there we go. We just solved the tangent problem on the circle just with geometry, right? Now, how about this calculus approach? Let's try out this calculus approach and make sure that it lines up, right? So let's see, then that's our exercise here. Let's see that this agrees with the limit definition of the derivative that we just wrote down up above. So how would I do this? Well, first thing I need to do, I'm going to say what the equation of the circle is. It's a unit circle, so x squared plus y squared equals 1. And I'm going to solve that for y because I need to think of it as a function, f of x. So just use algebra to solve for y. Subtract over the x squared, take square root. And this is, now it'll be different on, certainly on the bottom half, it'll be the negative square root instead of the positive square root. We'll just take the top half. We'll just work with the top half of the circle. We'll see that it agrees up there. You could do a similar calculation for the bottom half. So there's that y. So now let's calculate this limit. So let's see what we get. We have the limit as h goes to 0 of what? Well, we have f of x plus h minus f of x over h. Right? Now, this limit, you cannot evaluate this by just plugging in h. Basically, anytime you set up a difference quotient like this for the definition of derivative, if you try just plugging in h equals 0, you're going to get 0 over 0, right? Which is no good. That's not a well-defined quantity. So we need to simplify this limit somehow. So let's do this. Probably the easiest way to simplify this is to use a conjugate. So let's multiply the top and bottom by the same quantity, but with the sign flipped, right? And why am I doing that? I'm doing that because now on the top, I can use the difference of two squares formula. Right? So I'm multiplying the top and bottom by this quantity. So on the bottom, it just sort of sits there. But on the top, it now lets us use difference of two squares, which is going to get rid of all those square roots for me. Then I can actually expand out, just FOIL that x plus h squared, and that will be nice because those x squareds up top will cancel. And the ones also cancel, right? So there's actually a lot of cancellation up top. I'm left with not much. After the ones cancel, after the x squareds cancel, what do I have is just negative 2hx minus h squared. And this, I'm super glad that this happened because now I can factor an h out of the top and bottom and cancel it. So I get minus 2x minus h up top, and in the bottom, now I just have the roots. All right, well now I've resolved that whole It's not 0 over 0 anymore. Right now I can just plug in h equals 0. And I get negative 2x divided by what's in the bottom. I have, so now I'm just plugging in h equals 0. Right, so now we can set h equals 0. It doesn't just blow up to 0 over 0 anymore. If you look at the bottom though, this 0 isn't doing anything, so those two terms are the same. So I actually just get negative 2x divided by 2 of these roots. Then the 2's cancel. And I get the tangent, right? So this is the derivative. This is the slope of the tangent because this equals f prime from way up here, right? So now let's check and see if the calculus approach and the geometry approach gave us the same answer. They don't look the same, right? This is negative x over square root of 1 minus x squared by the calculus approach, right? So this is a slope of the tangent line, right? But now look up here. From geometry, what did we have as a slope of the tangent line? We said it was negative x over y. Ah, look at this. What's the formula for y on the circle? It's square root of x minus 1. Or sorry, square root of 1 minus x squared. Plug that in here for y. And what do you get? This. Right? So there we go. The geometry formula and the calculus formula are exactly the same if you just sub in the formula for the y coordinate in terms of x, right? So this actually matches what geometry told us, right? Because on the top half of the circle, y equals the square root of 1 minus x squared. So there we go. So there's an example of the definition of the derivative, evaluating a limit of a difference quotient, right? To calculate the slope of a tangent line. Now it happened to be the slope of a tangent line to a circle, which is something we could solve using just basic Euclidean geometry, right? And fortunately, the two approaches coincide. If they didn't, then we should throw away this definition of derivative and go find a new one, but they did, so we don't have to. All right, thanks.